Good morning, everybody. I'm Jason Freeman. I'm a little bit jet lagged, so please bear with me here. I don't know a lot of you here, so I thought I'd say a word or two about myself so you get some context. I have degrees in composition, undergraduate, master's, and doctorate, but I also have a strong thread of computer science through my education, and I have some industry experience as well. And I've been teaching at Georgia Tech since 2005, where I've really been trying to bring these threads together first in my creative work, where I do a lot of work with audience participation, live performance, stuff like the smartphone stuff that you'll be seeing tonight, though I'm not involved in that piece, but I do a lot of stuff like that, and real-time music notation and other things like that. But also over the last 6 or 7 years, I've been getting very involved in education research as well, which is what I'm going to talk about today. And at Georgia Tech is in the middle of Atlanta, a big city in the southeast of the United States. It's a big engineering university, 25,000 students. Music technology is a very, very small part of that. We have 35 students and 3 faculty. We started graduate programs about 8 years ago, a Master's of Science in Music Technology and then a PhD. We're working on a bachelor's degree in music technology as well, which hopefully will start next year. Our students come overwhelmingly from engineering backgrounds. Most of them already have degrees in electrical engineering or computer science. Our courses are a mix of kind of technically driven courses in DSP and music information retrieval, and more creatively oriented courses, interactive music, some analytics courses, and things like that. Most of them go and work in industry when they graduate. Places like Apple and Dolby and Grace Note and Pandora and Ableton and so on and so forth. Our research is pretty diverse amongst the faculty. I do a lot of work in kind of collaborative creativity and education. My colleague Gil Weinberg does robotic musicianship, like that robot on the picture up there. My other colleague Alexander Lorch does music information retrieval. And we do a lot of public-facing initiatives over the course of the year. We sponsor an international musical instrument competition every February, where we have an endowment. We give away $10,000 in prizes, the best new musical instruments. People come from around the world to compete in that. It's called the Guthman competition. We have a contemporary music ensemble that's in residence, Sonic Generator, that does a lot of collaborations involving technology and chamber music performance. And we present special events. We're hosting the Web Audio Conference this April, which was at EarCom last year, and it'll be at Georgia Tech this April. But today I really want to talk about one project I've been working on for several years now called Earsketch. And it has 3 different goals to it. It's a learning environment, and it's a pedagogy for teaching computer science and music together to high school students, to teenagers primarily. And I just wanted to walk through the context of it a little bit before I get into the project itself. So there's really 3 goals driving it. The biggest one is to broaden participation in computing, and I wanted to explain a little bit about what I mean by that. I'm not good at making pretty pictures and charts, so I borrowed some from code.org, which is an advocacy organization in Silicon Valley for computer science education. And they put these together to show what the situation is in the United States with computer science education. So we don't have national exams in the U.S. in subjects for high school students, but we do have something called the advanced placement of courses and exams, which is kind of the closest thing that we have to national exams. And so this is data from those exams that people all around the United States take every year, usually when they're 16, 17, 18 years old. And so these are how many people took it in all these different subjects. So you can see, lots of people take the history and English and science. This little orange thing down there, that's computer science. So 0.7% of the exams that students choose to take across all subjects are in computer science. So not that many students are studying computer science before they get to college, which is a problem in and of itself. But then if you look at the demographic breakdown of those students, only 15% of those students taking this exam in computer science are female, and only 8% of them are either African American or Hispanic, which means that this big orange thing there, that's basically white males. So there's not much diversity in who's studying and succeeding in computer science at the high school level. Another way to put this is of 3.6 million of these exams across all subjects that were taken across the United States a few years ago, only 3,000 were African American or Hispanic students in computer science. In many of the 50 states in the U.S., there were no African American or Hispanic students in the entire state that took the computer science exam. And the situation doesn't get much better when we get to college. So this is American universities here. Lots of people major in computer science. If you look at the enrollments at different CS programs across the country, they're bursting at the seams. They can't accommodate all the students that want to study. And then overall, if you look at college degrees in the U.S., women earn more college degrees than men. But if we look at college degrees in computer science, only 12% of them are going to women. The other 88% are going to men. So there's a lot of interest in trying to engage student populations that are not very engaged in computer science right now in the field, and this is a big part of where our work fits in, because we kind of feel like if we can't, there's a lot of problems across the pipeline of why there are not more female and minority leaders in the technology industry. But if we can't fix this at the beginning, at the educational level, I don't think we have much hope beyond that. And so our hypothesis here is that by using STEAM, by which I mean, so STEM is science, technology, engineering, and mathematics, and you add the A in and you get arts. So by using an arts plus technology kind of approach to teaching education, computing education at its introductory level, that combines computing and music in a way that's authentic and culturally relevant. I'm going to get back to those two words in a few minutes. That will engage a more diverse population of students in the field. And let me just give you a quick sense of what I'm talking about here. So this is a kind of classic intro CS assignment that I pulled off of the web. This is from codeacademy.com, one of the most popular websites for learning new programming languages online. And so this assignment is asking you to write something called a Pig Latin translator. Do any of you know what Pig Latin is, or is this some uniquely American thing that 8-year-olds do? Okay, so Pig Latin is a made-up language that little grade school kids like to use, where you take the first letter off of every word, you put it on the end, and then you add AY. So the word Python turns into Ithon Pay. Yeah, you can have lots of fun with this at lunch if you want. Anyway, so this assignment is to write a Pig Latin translator. You type in a word, it takes the first character off the front of it, puts it on the end, and adds AY. Great for basic string manipulation, all that kind of stuff you might want to learn in an intro CS class. Not really a creative assignment, though, because there's only one way to do this right? It either translates it right or it doesn't. And it's also, it's not something like if I wrote this in my Code Academy project, I'd go out and say, look world, look what I did. Because you Google Pig Latin translator online, and there's like 3 million of them on there, and they all do the exact same thing. So why would anyone care about the one that I just made? And once you're over the age of 8, nobody speaks Pig Latin anymore. So it's not really relevant to your life or interesting or personally meaningful in any way. So here's a sample Earsketch assignment. I didn't write this one. One of the teachers in one of our high school classrooms did. Kind of run-of-the-mill kind of standard thing. Compose a song, 24 measures long at least. You can do any style, any genre you want. There's some structural guidelines about different high-level sections, some certain API functions you have to include. You have to put in a for loop and an if statement and things like that to show that you've mastered some concepts. But other than that, it's totally open-ended. You can make it what you want. When students finish this, they want to share what they did with their friends. They're proud of what they did. It's personal and it's meaningful. And it's creative. So that's kind of the difference that we're setting up here. So that's the first goal, and the biggest one for us is broadening participation in computing and computer science. The next one is broadening access to music technology education. And what I mean by this is you all probably either have taught in a studio kind of like this or studied in a studio kind of like this. I couldn't find pictures online of any of the ones that I've taught or studied in. So this is from the University of Texas at Austin, but it made me salivate a little bit, all the analog synths there and digital mixer and all this stuff. Looks like a nice place to work. But there's only one chair in the room, right? So it's designed for just one person to use. And I believe this studio and a lot of others like it are designed primarily for introductory courses in electronic music, often not even for majors, but for people from other disciplines of music or even from other fields. And every institution I've ever been at has had a course like this. It used to be called the MIDI class. Now it's broadened. It's usually like music production techniques or something like that. And these are really popular courses, and they're really hard to get into because they're limited in size by access to this room. So they usually have 15 or maybe 20 students in them tops. When I was a graduate student at Columbia, and this was an undergraduate course, people would try to get in their first year of college, and if they were lucky, by the time they were seniors, 3 or 4 years later, they would actually be able to take it. At Georgia Tech, when we've taught courses that have been limited this way, there's online registration, and they fill up after 3 to 4 minutes usually once registration opens. So I've thought about this for many years, and kind of how frustrating that is that there's such a demand, but there's limited resources in terms of space and instructional resources to be able to offer this at a larger scale. And so one way that we can think about Earsketch is an environment that can help in this broader transition I think we're all seeing, moving away from dedicated studio space, especially in these introductory courses, towards students using their own laptops and readily available tools and headphones, and kind of scaling from the resource and space perspective that way. One thing that I particularly think is interesting about Earsketch from that perspective is that it borrows from a digital audio workstation approach. So it's very well suited for courses in which you start by teaching a DAW like GarageBand or Ableton Live or Logic or whatever it is, and then you transition into coding and algorithmic techniques because it connects the two very, very neatly together. And the second thing is that it's also a way to bring music technology into the computer science classroom. Because let's be honest, they have more resources than we do in music. There's a lot more students in those classes. There's a lot more instructional staff. And this is a way of bringing some element. It's not a replacement for music technology courses in pedagogy, but it's a way of bringing some of that element into another discipline where there's a lot of interest and there's a way to meet some of that demand. And then finally, the last motivation really comes out of my own personal artistic aesthetic and my work as a composer, which is this notion of evangelizing music making with technology. And the argument goes something like this. Very few people make music themselves anymore. I usually use as a benchmark the National Endowment for the Arts in the U.S. does a survey every 5 years on public participation in the arts. And one of the questions they ask is, have you played a musical instrument at least once in the last year? And 12% of Americans say yes. So that's a relatively low number. And we increasingly have this kind of division between music producers and music consumers. And technology is starting to go in the other direction with that, but we have to be careful as well. Particularly if we look at education of younger students as they're learning to play an instrument, as they're playing in a band or an orchestra, these educational experiences in schools, music is becoming less and less creative in the way that it's taught. And the example I love to bash is a program called Smart Music. This is made by the same people that make Finale, the music engraving software. It's very popular in school educational contexts. And it's a program that students can use either in a music lab at school or they can use it at home on their own computer. They see the music notation on the screen, they play it back against a metronome, and it marks every note green or red. It's green if you play it at the right time and you play the right pitch, and it's red if you don't. And so you can practice this over and over again, and it's a great practice tool for learning those notes. It'll show you the fingerings. It'll let you change the tempo as you're practicing, and so on and so forth. But it encourages this mindset where if all the notes are green, you're done, which of course is not true. That's the very beginning of learning to play music, is getting the notes right. But in the world of smart music and increasing the world of kind of K-12 bands and early educational experiences playing instruments, that's the end. So that's another kind of mindset that we're pushing against, trying to create more educational opportunities for creating music rather than just playing music and kind of rote reproduction. So in this way, Earsketch is kind of a sneaky way of working with music education. It's not taught by music teachers, which I'll get back to in a second. It's taught by computer science teachers, many of whom are actually not musicians themselves. There's no presumption of any pre-existing knowledge about music that goes into this, but a real focus on creativity and personal expression. So that these initial experiences of music making are ones that are really focused on individual expression, rather than on kind of this rote development of technical mastery, and approaching things from this other perspective. So those are the broad motivations that we had behind this project. And so now I want to talk about what it actually is and how it works. So I'm gonna introduce the different components of it, and then I'll walk through a bunch of examples in the environment itself. So we began working on Earsketch in 2011 at Georgia Tech, and there's a large team that I lead there from a lot of different disciplines. students and faculty and research scientists from music, from digital media, from computer science education experts, both teachers in classrooms and also people that do computer science education research, human-computer interaction, people that focus in developing evaluation instruments so that we can assess outcomes in classrooms and analyzing the resulting data, and so on and so forth. And what it is, like I said before, it's a STEAM learning environment, so the art plus technology, for introductory computer science. And it teaches all that in the context of music composition, remixing, and production. And so there's several different components to it. The first, actually, maybe I'll just walk through this. Yeah, okay, so the first component is a digital audio workstation. So the whole thing is driven by a DAW kind of paradigm. And the digital audio workstation in our world is some place where you view the results of your code execution. You see what it looks like, and you can play it back. There's a coding environment that is an API for both Python and JavaScript. Some of our classrooms use one, and some use the other. There's an audio loop library that we commission. It's about 4,000 loops from two great musicians, Richard Devine. He's a work records artist, experimental musician, but also a commercial sound designer that does work for Sony and a bunch of music technology companies and also Fortune 500 companies. And Young Guru, who's an audio engineer, DJ. He's engineered most of Jay-Z's albums, and he's his tour DJ as well. And then there's a curriculum, and these sounds are designed in kind of packs, so that, like in a program like GarageBand, where if you mix and match different sounds in the pack, everything kind of magically sounds okay together. And then there's a curriculum for introductory computer science, both student-facing materials, kind of like a textbook that's online, and teacher materials like lesson plans for day-by-day sample projects and quizzes and tests and so on. So the teachers have all the materials they need to walk into the classroom and use this. The environment looks like this. It's entirely web-based. And so you can see all these different components here. There's the DAW up here, the code editor here, the curriculum and the sidebar over here, and a sound browser over there where you can search and filter and find material you want to paste into your script. So the key design goals behind this for us, and these are the words I mentioned early on in the talk. The first one is authenticity. So it's really important for us that we connected what we were doing to how real people do things in the real world. And so that meant using real programming languages. Python and JavaScript are top 10 programming languages in industry and education. And so once students learn to code those in Earsketch, they can take those skills and start using them immediately someplace else. Now, we didn't want to use an industry standard DAW for a variety of reasons. One was cost to schools, and another was kind of the complexity of starting to get into some of those. But we did want to leverage those paradigms. So it's not like you walk into a professional recording studio and you see people using Earsketch, but you see them using Pro Tools or Logic. You see your friends on an iPad using GarageBand. This multi-track editing paradigm was really what we wanted to leverage. So again, the idea is that you can use in Earsketch and you learn, you can immediately apply to other contexts. Cultural relevance was also really important to us. We don't really support experimental electronic music, the kind of stuff that I write very well. I do actually perform and use Earsketch sometimes, but I'm not the target user. The target user is like a 14-year-old kid, and so the music that we provide, the loops that we provide them to remix, are in styles like dubstep and hip-hop, and things that matter to most of them. And we realize that we're never going to support everybody's genre preferences and stylistic preferences. So you can also upload your own content and use it within Earsketch. You can record your own sounds. And we started a partnership with SoundSnap a couple of months ago, so that there's another 200,000 sounds that students have access to beyond the ones that we've kind of hand curated for them. And it starts from a point of zero knowledge, both in CS, so you don't need to know how to code to start using Earsketch. You learn that along the way, but also from music. So we explicitly avoid music notation. We avoid MIDI because MIDI assumes that you have some kind of symbolic level of understanding of music or the ability to encode music as a series of note events. And everything is more at a loop level. We do introduce some rhythmic ideas about meter and tempo and so on, but at a very simple level. A lot of what we focus on is more about musical texture and musical form and things at a higher level of abstraction. Earsketch, like I said, is predominantly geared towards high school students. So that's in the U.S. is ages 14 to 18, more or less. In introductory computing courses, so the first experience that they might have being exposed to the idea of programming or coding. We've also used it in summer camps. We've used it in some college-level courses. We do teacher training at Georgia Tech and other places over the course of each year. And we have a healthy user base at this point. We have about 25,000 unique users from all 50 states in the U.S. and about 100 countries as well. A lot of schools adopting this in their classrooms. And the things that we cover are very run-of-the-mill topics in an introductory computer science course. And this is aligned with learning standards in the state of Georgia, and also a new kind of emerging national standard in the United States. So, data types, ints versus floats versus strings, things like that. Variables, constants, calling functions, and using arguments. Loops, like for loops, while loops. Conditionals, if statements, and the Boolean logic that goes into testing conditions, creating your own abstractions like defining your own functions, data structures, lists or arrays, randomness, operating on lists and strings, and all kinds of things like that. And the way we teach the music, each of these computing concepts, its introduction is really motivated by some musical thing that you want to do. For example, when we teach students to define their own functions, we motivate that by the introduction of musical form. And so we say, well, write one function for your A section, write another for your B section. Now you can repeat those in sequence. And then if you add arguments to those functions, you can introduce the idea that you can vary these sections each time that they repeat by calling them with different arguments. We cover copyright and fair use and Creative Commons a lot because students are already sampling from a loop library kind of by default when they're using Earsketch, and they have a lot of questions and concerns about sharing their own work, so we address that in curriculum. We cover music information retrieval in a very, very rudimentary way as well. I'll show you a little bit later. One thing that's missing from this list is pitch, harmony, and all that. We don't talk about that at all. We don't want to introduce that overhead and start bringing all of that in to bear. That's just it's too much in the context of what we're trying to do. And the Earsketch API is very simple. It's just about a dozen functions or so that map closely to things that you would do commonly in a digital audio workstation. Putting audio on a multi-track timeline. There's a step sequencing function where characters of a string map onto 16th notes of a rhythm. You can place effects on tracks and automate changes in parameters of those effects. And then there's some simple feature extraction for analyzing audio files. Like I said, it's entirely web-based. We actually did an earlier version of Earsketch that was built on top of Reaper, a great DAW. And what we found was that schools were having a lot of trouble installing it in their labs. The cost was one issue for them, but the other issue was just in order to install any new software program, they needed permission from their IT person, that needed permission from the district IT person, that needed permission from the state, and it took like 6 months to get any new application on the computer. And then it was sandboxed and it couldn't connect to the internet and all kinds of nonsense. So around the time that we were encountering these issues, Web Audio API got to a point that it was really robust and it was cross-browser. And so we started a new implementation a couple of years ago, entirely based on Web Audio API, entirely in the browser. So we use JavaScript and all, kind of pretty standard web stack on the client side. We have a very lightweight server that doesn't do much in the way of audio processing, but it's really just a database for user sessions and storage and so on and so forth. So that's Earsketch. And I know you haven't seen it yet, so I'm going to switch over to the web browser now and give you a sense of. It's not going to let me switch. Hang on. I better exit this. Okay, so here's Earsketch. I'm going to walk through a series of examples now to give you a sense of how it's designed and what it can do. So is this font size big enough? Can everybody see this in the back? Okay, good. So these are all Python examples, but in JavaScript they look pretty similar. So I initialize a new project. I said it's tempo, and these are some of the most common API functions here. I'm placing a sound from the sound browser, which is over here. I place that in to my DAW on track 1, going from measure 1 to 3. It'll match tempo, and it'll loop it as necessary to fill out whatever amount of time I've requested. Then I'm adding a volume effect on track 1, going from negative 60 dB at measure 1 to 0 dB at measure 3. And then this is one of these sequenced rhythms here. So the zeros here say play the note. The plus signs mean tie. If there were a minus sign in there, it would be a rest. And it's playing this tom sound on track 2. And it's looping it, so it'll play once on measure 1 and once on measure 2. And then... So you heard the fade in there, you see the step sequence rhythm down there, and the sound from the sample library there. So really kind of a bare bones script. But that's how students start learning, with these basics of I can use constants, I can define variables and figure out what the difference is between numbers and strings. I can call functions, and so on and so forth. And early student assignments look something like this, where they're defining a bunch of sounds from the sound library, and then it's just kind of a declarative style. There's no computational logic in here. It's just a bunch of successive function calls where they're creating a song. I can run this one. Hopefully I'm still connected to the internet, or this whole thing's going to fail. There we are. Okay, so just a bunch of calls with the same API function that I was showing you, putting things on successive tracks, adding effects, and so on. So this is what a first student project might look like, where they're very focused on the music and on these basic computational concepts. Yeah, I feel like I'm in a music store, like in the '80s, listening to a demo with that one. But anyway, that's because that was created by someone that was a kid back then on our team, rather than one of our students. I'll show you some real student examples in a minute. They sound much better. And then we get into more computational logic. So here's an example of string manipulations. So we define this basic string here, and then we can reverse the string so the beat plays backwards, or we can shuffle the order of its characters so that we're randomizing or shuffling around the beat. We can do a replacement of certain strings. So I'm taking all the rests here and replacing them with ties. Or we can introduce the concept of lists. So instead of having every sound in this beat be just this clap sound, I can send it a list of different sounds, or an array in other languages. And then these numbers become indexes into this list. So now we've learned how to create a list and to reference elements from it. So all these concepts coming forward just from this idea of I have a basic beat and I don't just want it to repeat forever. I want to vary it and I want to mix it around in different ways. And then we can get into more advanced examples later in the course. So here's an example where we introduce the idea of data sonification. So we have weather data. These are like the median temperatures in San Francisco over the course of a year, I think. It's a long list, right? Okay. And we learn how to step through a list with a for loop. We pull out every element, and then we map that onto a pitch shift effect. So when you actually run this, every 8 measures of music turns into this effect automation. So you can see the data from that array right there, and then of course you can hear it with the pitch shift. So if I bypass the effect, it's just a pad sound, right? The pitch doesn't change at all. But if I turn that on, so maybe not the most culturally relevant music in this particular example, but it gets the point across really well. And then I promised you I was going to show you how feature extraction works in our environment. We just support spectral centroid and RMS. So you give it a segment of an audio file and you say, give me the centroid or RMS. We used to support like a dozen different features. Nobody wanted to use them, so we just have these 2 basic ones now. So in this example, we have 2 different drum beats on 2 tracks, and every 16th note we walk through the sound file. We extract, I forget which feature it's on right now, centroid for that 16th note, and we basically then use a volume effect so that one of them was always at 0 dB and one of them's at negative 60, depending on which has a higher spectral centroid for that 16th note. So we create this kind of hybrid drum beat out of two existing drum beats this way. So, but if I solo the two tracks, you can hear. You can hear what's included from each. So this is teaching conditionals. We're doing a comparison. This idea that data is coming in, we're looking at it, we're doing something with it, and is a very, very vague introduction to the world of this notion that you can do analysis of audio and learn something from audio. A couple more quick examples I can show you. This is a very advanced example in the context of our curriculum, at least, where we teach recursion. So function calling itself over and over and over again. So we're teaching Cantor sets here, which is the idea that you have a line and you cut out the middle third of it, and then you have these 2/3 on the ends and you cut out the middle thirds of them, and you have all those and you cut out the middle thirds of them, and so on and so forth. So what's cool about this example is you can actually see that in the DAW when I run this. Because each successive track is another iteration of the Cantor set. Let me zoom in on this horizontally a little bit, and you can see here, so here's the whole line, and then the middle thirds have been erased, and the middle thirds of those, and the middle thirds of those. I think that's as many levels deep as we went here. So you get the picture. And here's an actual student project. This was written by a 15-year-old girl after studying Earsketch for about 6 weeks, and this particular project was about defining her own functions. So each section of music was a particular function. So you can see in the code here, she's got a section A, she's got a section B, she has something that's just applying effects to different tracks, and so on. So she's managed to explore this idea of abstraction. Okay, I'll stop it there. So once you've made a song like this in Earsketch, you can save it as a MP3. You can share it to SoundCloud. You can export it to Reaper, actually, as a multi-track project if you want, and so on. So there's a lot of ways to get it out of the environment and share it with other people in your class or beyond. The last thing I really wanted to cover today is some of the research findings that we've had from this project to see, does this actually do what we want? Does it engage students in computing and work towards broadening participation? And so the most recent study we did, we're underway with a larger one now, but I don't have results from that yet, is from 2013. We worked with about 100 students at a Metro Atlanta high school over 2 semesters. And half of them were enrolled in an intro to computing course where they did like web design and Photoshop and video editing and then programming. And the programming part was Earsketch. The other half were in an intro to music technology course. But it's funny, the school, they had this beautiful music technology lab. They had nobody to teach courses there because they had the money to build it but not to staff it. So the students signed up for a music technology course, and then they walked in the first day and the computer science teacher walked in. It's like, surprise. So the whole course was in Earsketch, actually, for that class. They were using the lab, but and they had an interest in music tech, but but they were learning it all through Earsketch. So in each of these courses, Earsketch was a module that was at least 10 weeks long. In that second course, it was the whole course. And we used three evaluation methodologies. We had a 20 multiple choice question content knowledge assessment to see what did they learn. We gave it to them at the beginning. We gave it to them at the end. We had about a 45 question attitude survey, which was built upon some existing evaluation instruments for computer science engagement and creativity in computer science as well. That asked them how did they feel before, how do they feel now, across a bunch of different constructs. And then we also did some focus groups with a subset of the students. And this is what we found. So these are all the different things that we measured from our surveys. I don't know where my mouse pointer went. These are all the things we measured from the surveys. Their confidence in computing, their enjoyment of it, their sense of its importance, their motivation to succeed, their sense of identity in the field, and their sense that computing and creativity are connected. And then their intention to persist in further studies. And what you see here, the up arrows mean there was statistical significance in increases across all of these things. So that's great. Things went up from before to after. And then the solid lines indicate that we found a significant relationship as well through a correlation and regression analysis. The dotted lines indicate there was a correlation, but that we didn't find anything through the regression that was statistically significant. So we're seeing a lot of important connections here to support this notion that participating in Earsketch leads to something, leads to increases in engagement and content knowledge in computing. Then we also looked across different demographic groups. So for this content knowledge assessment, there were statistically significant gains across all populations: female students, male students, minority students, majority students, and no significant differences in those gains. So everybody increased a lot, which you would expect because they come in, they have no knowledge of computing, so they do really badly on this assessment at the beginning, and then they learn something, so they do much better at the end. What's more interesting is when we start looking at this engagement survey. So these are all the different areas we measure in the engagement survey across here, and then the red bars are the female students before and after the course, and the blue bars are the male students before and after the course. And what you see across all of these is that the female students start off less engaged in each of these constructs than their male counterparts. These red bars are below the blue ones all across. At the end, though, they've gained much more than the male students. They're actually higher than the male students in all 7 of these constructs after the course. And the ones with stars in them, that difference is statistically significant, via a t-test. So we know that there's significance to the fact that the females gain more than the male students. You can look at it this way as well. This is the magnitude of the change, how much female students increased as compared to males in each construct. So you can see that the magnitude of the change is much higher across each of these. And so what the story we're getting out of that is that female students started off less engaged in computing. They ended up more engaged in computing. There's some significance behind that. So that encourages us that we're seeing something that's really meaningful here. And if we go back to our focus groups and some of the free response comments we got on the surveys, we see some evidence that this that suggests that this goes back to this notion of authenticity and cultural relevance that I was talking about earlier. These are examples of things that we saw from lots of students. We got to express my ideas, and it was fun and inspiring to see that I could be good at computing. I liked learning how music is made, how we can learn and get good at doing things that people in the industry do now. Enjoyed making my own music tracks that people, including myself, actually liked. It gives me choices for college and careers. So a lot of stuff that encourages us to continue in this work and to try to further learn about why we're seeing these kinds of gains and how much we can replicate them at larger scales. Very briefly, I'm going to skip over most of this. We've also put this into a MOOC, a massive open online course on Coursera, to try to engage people at an even broader level. MOOCs kind of suck. They're really hard to fit in, especially on a platform like Coursera that doesn't really get the fact that you might want people to collaborate and interact with their peers at all. So the MOOC is half learning in a DAW context and half learning Earsketch and computational music. So we lose lots of stuff, peer interaction, instructor interaction, and so on, but we still have this authenticity and cultural relevance. So what happens in that context? The key question that we had was, could we replicate these kinds of gains in engagement? And the answer is sort of. we gave the same survey to MOOC students that we gave to high school students. We did see that the female students had much bigger gains than the male students. However, if you look here, they're starting off way below the male students here, and they're still below the male students at the end in terms of engagement. So this was a very small scale study. We're collecting some more data right now. We got a new iteration of the MOOC that just launched a few weeks ago. So we want to be able to see what more significance we can see when we have a pool of 1,000 student data points we're looking at instead of 100 or 150. We're working on a lot of stuff with Earsketch right now, really looking at the work we've done to date as a foundation for branching out in a lot of different directions. We're developing a blocks-based version of Earsketch where it's graphical coding instead of text-based coding in Python or JavaScript, so that we can reach out to younger students in the 8 to 12 age range that might not be able to do text coding yet. We've just wrapped up integrating processing, actually a library called P5, which is a JavaScript version of processing, into Earsketch, and that'll be coming out in our next release, so that people can do audio-visual coding with Earsketch, linking the audio to animation or visuals or whatever else, and vice versa. We just released some updates that support live coding with Earsketch as well. I gave a performance about a month ago. The first time I've live coded in about a decade, but it was fun. So you can live code in Earsketch now too, and we're just starting to explore what that means pedagogically. We kind of did it because it was easy to add to the environment, but we're not quite sure how that fits into classrooms yet. So that's an open question. We're building a version for museums. It's a tabletop interaction, sort of supporting more kind of casual interactions. Tablet version. It hooks out to physical computing and building interfaces into the environment with Arduinos or lily pads or things like that. And we're also spending a lot of time this year particularly thinking about how people collaborate with Earsketch and how to better support collaboration. Kind of really bringing that out. The MOOC is one way that started us thinking about that. So if you're not in a classroom where everyone's sitting together or where a teacher's really good at facilitating student collaboration, how can you help enable some of that through the technology itself? To help people find out what others are doing and build on other people's work and so on. The curriculum, we're aligning with a new national standard in the United States for computer science education, building kind of more self-study things that you can go online and just learn it yourself instead of in a classroom. We're partnering with the University in Atlanta to develop a curriculum more geared towards college students and high school students. A summer camp model where we have high school students that have studied Earsketch actually running a summer camp for younger students to reach out to them at these earlier grades. And really thinking about how we do our teacher training as well. We usually do every summer a week-long session that's limited to about 20, 25 participants. We want to be able to scale that. So how can we use online resources and combine that with face-to-face training to be able to train more teachers? And then there's a huge part of our project that's research focused. Building on the results I showed you before, updating some of our research instruments, a much more expansive way of looking at how we measure creativity, students' perception of creativity. We have a new knowledge assessment as well that's facilitating comparison studies. So our current one is just about Earsketch, and the questions are all kind of grounded in Earsketch. The new one is language agnostic, so it can be given to students in any computer science course, no matter what language they're learning or what environment they're using. So we're doing that to study differences between what we're seeing in Earsketch classrooms and non-Earsketch classrooms. And we're also using a technique called agent-based modeling to tease out kind of the differences between different schools, because education is a very complex system with different things involved: the teacher, the student, the administration, the district, all kinds of different factors that influence what happens in a classroom and what the outcomes are. So agent-based modeling tries to embrace that complexity and kind of tease out what the important factors are, what's really contributing to the outcomes that we're seeing, so we can use that to inform how we develop the project itself further, and also kind of make recommendations for where are the best places or what are the necessary preconditions that a school needs to be able to use an art and technology intervention like Earsketch with some success. So lots of exciting work that we're up to right now. You can learn more about the project earsketch.gottech.edu. It's free, it's online, the curriculum's under Creative Commons. My website, if you want to learn about kind of the more creative side of my work. And GTCMT is the Georgia Tech Center for Music Technology, that last URL that summarizes all of our research in music technology at Georgia Tech and has information about our degree programs as well. I couldn't fit everybody's name on the project on the slide. There's about 30 people that work on this in various capacities, but the website lists them all, and these are the main people that work on the project with me. Yeah, that's about it. Thank you very much. Yes.
Yeah, it's a great talk, thanks. I happen to be teaching computer science and also participating in a computer music class, and I was wondering whether you have any idea about the issue. One of the issues that distinguishes computer science from computer music is the science word, which in my mind means both problem solving and correctness, and trying to figure out whether your algorithm implements what you have in mind. And these things actually don't fit into the more creative way of using computers. Have you thought about a way of introducing these two notions into your curriculum?
Yeah, it's interesting. So the word computer science itself has been of great contention on our team, and sometimes we use, like when we ask students how they feel, do we ask them about computer science? They don't even know what that means. So do we use computer science? We often end up using coding or programming or computing, which is a little bit different from computer science. But I think what you're talking about is really what I would call computational thinking, this logic and this kind of puzzle-solving kind of mentality in intro CS, and we're going through this debate right now with our university partner, where we're developing some curriculum that's geared towards a more college-level course, and they're saying, well, it's great to have these open-ended projects where people can do whatever they want within certain constraints, but we want something that can be auto-graded. We want something where there's, they really have to solve a problem in order to make, to get the result. And so we're creating a series of kind of graded tutorials for them right now and assignments that follow that paradigm as an experiment. I'm not sure where it's going to go yet.
It seems to me that if you have no constraints whatsoever,
yes,
then you have no way to judge. So maybe adding constraints to the assignments you give to students, which you sort of have. You say, I want this structure to be this and that.
Yeah, I mean, the example I gave you was particularly open-ended. Some of them are more constrained than that. But we're looking at, well, what happens if we give 5 or 6 very short assignments where you have to do exactly something and kind of figure out a solution in order to get there. And then once you've solved those give you the building blocks you need to do a larger project where you have a lot more freedom. So that's definitely a paradigm that we're looking at as a way to kind of bridge that gap. And it's an issue that we've certainly been discussing.
Trying to pretend that computer science is pretty much computer music, and then that's going to be
right.
fun and happy. And
at the high school level, it's not as much of a concern for us because really, if you look at the learning objectives that we're trying to tackle at the high school level, the coding, being able to code is what's really important there, and having awareness of what computing is as a field. The engagement is much more important than the content knowledge at that level.
Well, this question relates to that. Have you been hitting walls while experimenting with Earsketch in high school education? So, for instance, recursion, that the students just wouldn't get it. I mean,
yeah. So recursion.
I want to bring you over to the dark side of this.
Yeah. So recursion isn't even part of our core curriculum anymore. It's an optional unit, kind of out there in the ether. But what we find is when we get to lists are the first place that we start to see a bifurcation. Some people get it right away, and some people don't. And that's one of the reasons that I've been pushing our team to introduce it the way I showed you today, inside of those beats, where it's just I create a list and then I reference it before we start bringing looping in with lists or anything else like that, as a gentle introduction. So that's the first place where we really see some challenge. Yes. I think that the other challenge that we see at the high school level is that there's a huge shortage of qualified computer science teachers because we don't pay high school teachers very well. And if you are good at computer science, you can make 5 times as much money doing anything else than teaching. And then, like in the state of Georgia, to be a computer science teacher, you have to be accredited as a business teacher. So if you're a math teacher, you're not allowed to teach computer science. But if you're like the typing teacher, then you're good. So we get a lot of teachers in the classroom that have very limited skills themselves, and we have to do a bunch of training just to get them to the point that we want the students to be at. So some of them struggle, not so much with lists, but like if we threw recursion at them, a bunch of these teachers would freak out. Yeah?
In my experience, the students interested in composition, with so much specialist software as the DAW is available, they take the path of least resistance. So I think an interesting barometer may be what they do outside of the classroom,
yeah.
How much of this they take into their own practice. Do you have any indication of that?
We see things that they share on SoundCloud sometimes, or we see larger projects that they might do. I think that your point is very well taken, and I think that some students, one of the things that teachers tell us sometimes is that you can make so much music so quickly in the environment that sometimes it's hard to motivate them to do the extra computational things once they get the core API down, the kind of declarative thing. And so one of the things we're working on right now is actually, should we make it harder at the beginning? Like, if you want to loop a sound, should you have to write a loop, or should we be auto looping it for you, and things like that. I know. There are actually some ways we already have deliberately crippled the language to make sure that you have to, say use loops if you want something to repeat, because we want to force them out of that paradigm. But also, the burden's on us in a lot of ways, because we want to make sure that we make arguments in our curriculum that every new computational concept we introduce is motivated by a musical goal, and saying, look at what you can do, look at how you can do something you couldn't do before, you could do it so much easier than you could before, you could experiment more rapidly, and I think that a lot of that burden comes back to us to make the case for each of these things. I don't like crippling the tools we give just to make that case. Usually we want to show how the computation can really help them. I'm looking at a time on my PowerPoint here, so yeah.
Can you tell us a little bit about the implementation? Is it all client side, or is it mixed with the server?
It's 95% client side. The only audio processing that happens on the server right now is time stretching of the samples. So when you request the sample, you requested a particular tempo, and time stretches it before it returns it to you. And we're actually in the process of moving that to the client as well. So really, once that migrates over, the only thing the server is doing is it's serving the audio files. It's user session state. It's storing your code and stuff like that. Everything else is on the client. We have one server, and we wanted to be able to support growth. So that was one factor, and also in terms of latency of the interaction and keeping it very responsive. The more that we put in the client, the better we found that experience was. Okay, well, thank you all very much.